Hello guys. Welcome to the 2002 AP exam. So this is kind of cool for you. It's their first real exam that students took before. And we'll be going through questions 1 through 3 on this first part of the video. Okay, first off here it says, let's see here. In 1915, Einstein's theory predicted the curvature of space denoted by, I don't know how to say that, excuse my ignorance, but I wrote that symbol best I could, was 1, while Newtonian theory predicted it was 0. Since 1915, scientists have repeatedly found estimates of that variable using various methods and procedures. Each estimate has a margin of error. Figure out the figure below displays that estimate for each of the 21 experiments. So these are confidence intervals, you can see from there, and these are the intervals. So in each interval, wherever it goes from here to here, are the possibilities, okay, of that value, okay? If you'll notice that 0, the predicted value from Newtonian's, the Newtonian work there, none of those intervals contain that. So there's basically no evidence stating that. And then the other predictions for Einstein's predicting it at 1, and 1's very good. It's almost in all the intervals as a possibility. And if you notice later on, okay, the estimates are becoming more recent and becoming more and more precise because our intervals, the actual size is literally becoming smaller and smaller, showing the lesser variability in those answers. Okay, so let's have a look really quick. All right, I'll show you my answers in a minute. Based on the display, describe how the position has changed over time, the precision. Okay, the precision, excuse me, has increased dramatically. Look at the variability on these ones back here, and now it's getting narrow and narrow and narrow. Okay, so I'm going to say that the precision has increased dramatically over time, and we can see that by the fact that the intervals become smaller and smaller as we go to the more recent experiments. All right, write a few sentences describing the strength of evidence experiments provide for the claim from Newtonian theory that that value is 0. Okay, and again, there is no evidence because 0 is not a possibility. Okay, and I want to say how I know that, even though it's obvious to you, I'm sure, because 0 is not a possibility or contained in any of the intervals that we found. All right, finally, write a few sentences describing the strength of evidence experiments provide for the claim of Einstein's theory that that variable equals 1. I believe it stands for the curvature of space, if I'm not mistaken. Your response must include justification based on display. So you can't just say maybe you know that it is 1, and you can't just say something like that. You're basing it off this evidence here. Okay? All right, we have very strong evidence again that that value is 1 because 1 is here. And remember on these intervals, it's just as likely down there as anywhere on the interval. So 1 is a possibility on almost every interval there is, except for 1, 2, 3, 4 of them, okay? And probably more importantly, as we get closer and closer and our results have less and less variability, as we get more and more precise, you can see that they really look like the answer is 1 or very close to 1. All right? So I have my answer for that shown. Put that up here. Here's my first answer. I'll let you read that. Key things we talk about, the variability or precision is fine, is much smaller. Well, the variability is much smaller, and the precision has improved or increased, okay? And then how do we know that? By observing the fact that the interval estimates are getting narrower and narrower as time becomes more recent. Those are key factors in our answer. Okay, part B, evidence supporting the claim that the value is 0. There is no evidence supporting the claim that the value equals 0, and that is not a possibility within any of the intervals given. Okay, and finally C, there's strong evidence supporting the claim that that variable, is 1. It is within almost all the intervals shown, meaning there's a possibility in each of those cases. Also, in the more recent intervals where there is less variability, it looks like the true value must be 1 or very close to 1. Okay, so question number 1. Down. All right, let's go to 2. See what 2 is all about. Another experiment here, okay? A manufacturer of boots plans to conduct an experiment to compare a new method of waterproofing to the current method. The appearance of the boots is not changed by either method. That's important because if I'm wearing the boots, I wouldn't know if they're treated or not. I can't tell. The company recruits 100 volunteers in Seattle, where it rains frequently, to wear the boots as they normally would for 6 months. At the end of the 6 months, the boots would be returned to the company to be evaluated for water damage. Okay, describe a design for this experiment that uses 100 volunteers, include a few sentences on how it would be implemented, and then could our design be double blind? Okay, things we want to do. I don't want the people to wear one pair of boots for 3 months and the other for 3 months, because during that time in Seattle, the weather probably changes. Probably one of those months has more rain than the other, so, or one of those sets of 3 months, I should say. So we really want to have them change intermittently. We talked about it today in class that we need to have randomization. My idea was to have 2 pairs of boots that I would give each participant, and each of those pairs, one pair would have the right boot treated, and the other pair would have the left boot treated, and then each participant would flip a coin every day, and that would determine which pair they wear. So there would be lots of variability in the different weather patterns and all that. We wouldn't be doing all in one time of the year and all in the other. Those would be mixed up. The people wouldn't know which ones they're wearing, okay, and by wearing a right and left, they would each boot would have the exact same wear as the other boot, the treated or the non-treatment, okay? So that is my plan. Involves a lot of good things there. Let's see what I wrote here. Okay. Each of the volunteers would be given a pair of boots, which the right boot was treated, and the second pair, which the left boot was treated. Participants would not know which of the boots are treated, since the treatment does not affect the color. Each day, each volunteer would flip a coin. Okay, so some way you want to say that they're randomly selected, those boots, and how you would do that. So flipping coins is a really easy way to decide which pair of boots they would wear that day. At the end of the 6-month period, the boots would be collected and evaluated. Part B, could our experiment be double-blinded? Sure. We already talked about the people wearing the boots aren't going to know which boot is treated or not. They can't tell by the color. And then to be double-blinded, those people running the experiment and possibly like distributing the boots and also measuring the wear of those boots or how they did would not know which boots were which until the results were compiled at the end. Okay, and that should be here, part B. It could be double-blinded. There we are. The wearers, the boots are not aware the particular boot has been treated or not, and if the test administrator is unaware of which boots have been treated as well. That's very simple. Okay, question number 2. All right, let's go to 3. I was thinking about, okay, some things to note, like we've done, you're doing a few of them here. Typically there's some kind of describing of a distribution here. This is related, it's a little different, but there's something like that. The ones we've done so far, there's some talk of an experiment and how to design it. Okay, that'll be one of your questions most likely. Okay, and then we're coming down here and there should be some calculations done. This is going to be like a normal CDF type situation here. Okay, so we have 4, again, very normal and very typical that you have binomial probability. We talked about in class as well within our problems here. And in 1 through 5, like you will have a hypothesis test of some sort for sure, or a confidence interval. Almost always some type of hypothesis test. Okay. Remember whenever they say that they're looking, is there sufficient evidence to show there's evidence? Then we're running a hypothesis test for sure. Okay, there are 4 runners on the new high school team. The team is planning to participate in a race which each runner runs a mile. The team time is the sum of the individual times of the 4 runners. That'll be like our expected value. That'll be the sum of the times. Each runner is expected to run this time, and then the total race would be the sum of all those times that we would expect, assuming there's no delay with the handoff, right? Assume the individual times of 4 runners are independent. That's good. That helps us do meet our like condition. Kind of the individual times and minutes of the runners in similar races are approximately normally distributed. We're looking for that. That means I'm going to do normal CDF. It's already normally distributed. It means I don't really have to do any conditions here for a group. Okay, it says runner 3 thinks he can run a mile in less than 4.2 minutes in the next race. Is this likely to happen? So we're going to do normal CDF and find the probability that he will run less than 4.2. Here's runner number 3's stats right there. It's 1 runner. I don't need to calculate a new standard deviation. So part A, here we go. Okay, runner 3 has a mean of 4.5, standard deviation of 1.14, and we're looking at the likelihood he'll run under 4.2 minutes. Probably that our sample value will be less than 4.2. Here is my picture. Okay, and I'm just going to go normal CDF, and it's 0.0161, and I believe they asked me if it would be likely, and I would say it is unlikely. Or if it asked me just what is the likelihood, then the likelihood that he will run the mile under 4.2 minutes is 0.0161. Let me go back and check our question. Okay, is this likely to happen? So I'm going to say that is not likely to happen. Okay, because the probability is less than 5%, which is considered a rare event. All right? Okay. 3B, the distribution of possible times is approximately normal for the whole group. What are the mean and standard deviation of this whole distribution for all 4 runners? Okay, here we go with that. That should be a nice, easy one for us. Okay, for the whole group, I have the values of each runner, the mean and the standard deviation. The expected value of runner 1, 2, 3, and 4. You wouldn't necessarily have to write that, but you need to show the arithmetic again. I'm just going to add those up. You must show that math equals 18.9 minutes. Okay, our standard deviation, in this case, we're adding the times together, so it's not a tricky thing. But remember that the variances always add, no matter what. So these are the standard deviations. I square those to get the variance, and I'm going to add those together. Okay, so the variation of x1 plus x2, x3, x4 are those variances added together, and the standard deviation is the square root of that variance, which ends up being 0.3003. And I would just answer in a sentence that the mean expected time for the 4 runners would be 18.9 minutes with a standard deviation of 0.3003 minutes. Notice that they have units on them, and the standard deviation always has the same units, as does the mean. Okay, finally, last question. Suppose the team's best time is 18.4. What's the probability that it will beat its own best time in the next race? Okay, so we've got, and this is very typical, you calculate the mean and standard deviation for the group, and now we're going to use it. Okay, so the mean time is 18.9 with that standard deviation for all 4 runners, and they want to know the likelihood we're going to run less than 18.4 to beat their record. Okay, so I have that information there. They're probably at X bar. Our sample is less than 18.4. I just do normal CDF. Okay, and that is 0.0480. They asked me the likelihood of it. The likelihood is 0.0480 that they will beat their previous team record. All right, and that is it for 1 through 3. Thank you, guys.